This video covers learning outcome number 2, which is about using histograms to infer characteristics of data. So there are a lot of important uses of histograms, but the most important use is that it visually displays the shape of the distribution. We talked about CV dot briefly, those 5 characteristics of data that are so important. They're sort of the defining characteristics of a data set that we're typically trying to find when we're using descriptive statistics. One of those is the distribution. So the histogram is a graph of the frequency distribution or the relative frequency distribution, and it's visually showing us what that data looks like. So it's displaying the shape of the distribution. That's the most important use of the histogram. And by looking at that shape, we can determine whether that data is approximately normally distributed. So we can see that low, high, low pattern that we talked about when we were referring to frequency distributions. We can also see whether the histogram itself is symmetrical just by glancing at it. We can see if it has that low, high, low shape and if it's symmetric on both sides. So we don't even have to look at tables of numbers anymore. Instead of looking at tables of numbers, we can look at these graphs, which are like bar graphs, but they're displaying that shape of the distribution, which is a histogram. Histograms also show us the location of the center of the data, or one measure of center, when you're looking at the histogram and you see that tallest column. So you see that most of the data was lying in a particular class. That is one measure of center, and we'll be able to see that in our histograms. We also see the spread of the data. So if we just look at that horizontal axis, we can see like the lowest class values that are included in our data set, as well as the highest class values. We see where we start and where we stop and how that data is spread out. You can also see if it's concentrated very close to each other. And lastly, it helps us to identify outliers. So remember that CV dot were those 5 characteristics of data. C is for center. We get to see the center with a histogram. V is for variation, which has something to do with that spread. Are the data sort of spread out, or are they all concentrated around a particular value or set of values or range of values? And we also get to see that shape of the distribution. You know, do we have one peak? Do we have 2 peaks? And then we also can visualize, visually identify, outliers by looking at maybe values in a class that exist in our data set, and then there might be no other data nearby. So the classes nearby might not have any elements in them at all, or might have a frequency of 0. So this is a great way to visualize that frequency distribution or relative frequency distribution. So here's an example. We've got our eruption times, durations of eruptions of Old Faithful, same eruption times as before. Right away I see I've got an outlier. That one eruption time that had a duration between 125 seconds and 149 seconds. Like, that's an outlier, because all of the other eruption times tend to be over here on the right side of the graph. There are no eruptions that last between 150 seconds and 199 seconds. So we see that as far as a measure of center is concerned, like, we can see that the center of the data set seems to be over here in this class. We've got 34 eruption times that were between 225 seconds and 249 seconds. So it's represented by this tallest column in our histogram. That's a measure of center. We can see that the distribution itself, when we look at it, including that outlier, most of it is on the right of the screen. So that's not symmetric. Therefore, this distribution is not approximately normal. We don't have that low, high, low pattern with the symmetry that we were expecting. So we were able to infer outliers. We were able to infer the center. And then we can see the spread of the data and the shape of the distribution itself just by looking at this graph. Similarly, with the McDonald's lunch service times, we can see that the center is right here with this tallest column. Most McDonald's lunch service times are between 125 seconds and 174 seconds long, at least in our sample. So the one measure of center might be a McDonald's lunch service time between that 124 and that 174 seconds. Let's see, what else? We see the shape of the distribution. It kind of looks like a normal distribution, but it's not symmetric, not around like a middle point. It looks like most of the data is over here on this low end as opposed to being over here, or as opposed to being in the middle. So even though it kind of looks like a normal distribution, since most of the data is at the low end, that makes this not a normal distribution. We're going to talk about distributions that look like this more in a little bit. But we see the center, we see the shape of the distribution. We don't see any outliers, but this is excellent as a graphic. It gives us a picture of what McDonald's lunch service times actually look like. We know most of them lie up here, and then some of them, few of them, lie within this 174 or 175 to 324 seconds range. Now the rest of this is about common distribution shapes. For the most part, we're interested in normal distributions. We like to have normal distributions or normally distributed data. The first type is this normally distributed data, which has this bell shape. Then we're going to talk about uniform distributions, which look kind of like this. Then you have data that's skewed to the right, and then you have data that's skewed to the left. We'll talk about each of these in turn as common distribution shapes. So the first one is that normal distribution. Because this data, this is a data set of arm circumferences that are measured in centimeters, has approximately a bell shape. We would say that arm circumferences appear to be approximately normal. We've got that low, high, low pattern, and there's symmetry around the middle. So we've got that middle value, that center value seems to be close to 32 centimeters. And since we have symmetry around the middle and the low, high, low pattern, we see that as a probable normal, or data that come from a probable normal distribution. And many statistical methods will require that the data is approximately normally distributed. So we're looking for this low, high, low pattern. There's a much better way to determine whether a particular data set is normally distributed. But this is a quick way to, at a glance, determine whether that data is normally distributed. If you see the low, high, low, and the symmetry about that center, a symmetry about the middle of that range of values that are on the bottom on that horizontal axis, then we would say that the data are normally distributed. Another type of distribution that comes up pretty often is a uniform distribution. If you look at the graph, it looks like a giant rectangle, and it kind of is. Notice that all of the bars in the histogram have similar heights. Like, this is what I would expect if I were rolling a die and I was using a fair die. If I kept doing that over and over and over again, and then I was tallying how many ones I got and how many twos, threes, fours, fives, and sixes I got, well, I would expect 1 out of 6 times approximately to get a 1, and 1 out of 6 times approximately to get a 2, and 1 out of 6 times approximately to get a 3. So as I do this over and over again, after a really long time, the frequencies of the 1s, 2s, 3s, 4s, 5s, and 6s aren't going to be exactly the same, but they should be similar. If it's truly a fair die, it should be similar. And the same thing is true for something like this. Looks like we've got digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I mentioned that earlier. This histogram has a roughly rectangular shape whenever it's uniform. Another data set that you would expect to be uniformly distributed is last digits of measured data. So if you measured something, like if you were measuring those arm circumferences with, I don't know, I guess a tape measure, and then you were looking at that last digit, if you were being as accurate as possible, you would expect that a last digit of 1 would appear just as many times as the last digit of 3, or a last digit of 7, or a last digit of 5. All of those, I would expect them to appear about the same number of times. So if we're expecting the same probability, if we're expecting similar outcomes for each of the classes, then the distribution tends to be uniform, which will look something like this. A uniform distribution, a true uniform distribution, would have a straight line at the top where every frequency is exactly the same. Now, in practice, we don't tend to see that, of course. As you're collecting data, sometimes just through chance, some classes have slightly lower, slightly higher frequencies than others. But the general shape, if you sort of squint and you back up, it looks like a big rectangle because all those frequencies are roughly the same. Now, skewness is another property of data. We say that a distribution of data is skewed if it's not symmetric and it extends more to one side than the other. So here's an example. I've got data that is skewed to the right. Now, some students have trouble with this. They think this is skewed to the left because more of the data lies on the left than it does on the right. But this is how you want to remember it. We say that data is skewed to the right or positively skewed if it has a longer right tail. So this side is called the right tail, and this side is called the left tail. If the right tail is longer, we say it's skewed to the right. Even though you might think that more of the data is on the left, don't think of it that way. Think of the tail as being longer on the right. So this is data that is skewed to the right. Now, if I gave you a really hard statistics test so that most of the scores were low, then we might see data that's skewed to the right. But ideally, I would give you a statistics test that was not only fair, but one that you felt very well prepared for. And instead of being skewed to the right, we would want data that are skewed to the left. So skewed to the left looks like this. Oh, oops, before we go on to skewed to the left, here's some data that is skewed to the right. We've got that McDonald's lunch service times. It's skewed to the right because most of the data sort of lies on the left of the table, and we have that long right tail. But we would want this data, this McDonald's lunch service times, to be skewed to the right. We would want the lunch service times to be short. When you're going out for fast food, the idea is that it's fast. And the fact that it's skewed to the left like this, maybe that's a very good sign that those service times tend to be low. So that is an example where being skewed to the right was actually a good thing. I wouldn't want your test scores to be skewed to the right because that would mean your test scores were more low than they are high. Now, skewed to the left or negatively skewed looks like this. And again, students get confused because more of the data is on the right. You don't want to think about it that way. When you say skewed to the left, what you're saying is that the left tail is longer. So this side is longer than this side, so this is skewed to the left. When I graph your test scores, my hope is that the data are skewed to the left. I hope most of my students are getting A's and B's. So the very high grades have the highest frequencies. Like that would be ideal. Most professors would expect that bell-shaped distribution with most people getting C's and some people getting A's and B's and some people getting D's and F's. That's normal and to be expected. But ideally, if I prepared you well for the test, my hope is that it's going to be a skew to the left. We're going to have more grades in that A, B, and C range, and preferably in the A and B range. So I would want the data to be skewed to the left, which means we'd have this long left tail. Which means, yeah, most of the scores would be high. Another example of data that's skewed to the left, at least with the outlier included in our data set, is the data for the eruption times of Old Faithful. Because we have that outlier in the data set, it looks like this data is skewed to the left. It has that long left tail. Now, even if we omitted the outlier, if we just focused on the data over here on this right side, notice that there's no symmetry around that middle class, that class that ranges from 225 seconds to 249 seconds. The other eruption times, most of the other eruption times were greater than that 225 to 249 seconds. They were in the next class up, not the class down. There's no symmetry around this one. There were only 3 eruptions that were in the class before it, and there were 12 eruptions in the class after it. So this really is skewed to the left. It has that long left tail. And even if we ignored this, it would have a longer left tail than a right tail because of the lack of symmetry on the left and right of that, that high frequency class right here, which we can think of as a measure of center, which we'll talk about in the next chapter. Okay, so let's review again the important uses of a histogram. Histograms allow us to visually display the shape of the distribution. We're looking for that bell shape. We want it to be normally distributed most of the time. Now, if it happens to not be normally distributed, that's often insightful, like it was insightful for the McDonald's service times, and like it was insightful for the duration times of eruptions of Old Faithful. It tells us something that the data is skewed to the left or skewed to the right. But a histogram, if we graph it, this will allow us to determine just at a glance whether that data is approximately normally distributed. So we're looking for low, high, low pattern, and we're also looking for symmetry around the middle. This also shows us the location of the center of the data. One measure of center is going to be associated with that high frequency class, that high point on your histogram. That's going to be a measure of center. It also shows the spread of the data. Are the data concentrated in a certain area or in a certain class, or are they spread out more or spread out less? We can see that when we look at a histogram. And it also allows us to identify any outliers. If there are any frequencies or any data points that are in classes by themselves or with very few others far away from all the other data, we'll see that in the histogram. And then in this video, we also discussed those 4 common distribution shapes. So our first one is that normal distribution with that low, high, low pattern and symmetry about that middle point. The highest bar is sort of in the middle, highest couple of bars are in the middle. We've got a uniform distribution. That's a distribution where you would expect all of the classes to have similar frequencies. Or if you were to create a frequency distribution and all the classes had similar frequencies, we'd say that's approximately uniform. So for some reason, all of those classes are giving us approximately the same, are appearing at approximately the same, I want to say rate, but that might not be the right word, approximately the same number of times. So that would be a uniform distribution. Now, if it has a long right tail, we call it skewed to the right. That means most of the data is low. And then if it has a long left tail, that's skewed to the left. That means the majority of the data is high. So this is skewed to the right and this is skewed to the left. Please let me know if you have any questions, and I will see you in the next video.